Okay, so let's just get started then. Let's do a recap from last time to refamiliarize us with some of the ideas. So we'll just use a quick little example to refresh us. So let A be the set 1, 2, 3, 4, and let B be the set 3, 4, 5, 6. And then let's just write out each of these to remind ourselves of what these set operations were. So we've got two sets here. This is a set operation. What set operation is this?
Union.
Union. And union is all the elements that are in A or B. It's like the set version of OR. And so A union B, what are the elements in here? 1, 2, 3, 4, 5, 6. Everything that's in A or B. Right? Pretty straightforward. This one, intersection, it's like the set version of and. It's everything that's in A and in B. So this is going to be the set 3, 4. Perfect. All right. And then set difference. We remember how to calculate a set difference?
Everything that's in A that's not
Everything in A that's not
in B.
in B. So what's this set going to be?
1, 2.
The set 1, 2. And notice that this is not the same thing as a set B minus A. What's a set B minus A equal to? 5, 6. Perfect. And then the last set operation that we had was the complement. Something like A complement. And that's equal to the set of everything that's not in A. Now, with set complement, it only makes sense if it's given in some context where you know the universe you're in. Outside of that, the only thing I can say A complement is it's the set of everything that's not 1, 2, 3, or 4. So we can't really write it out explicitly here because we don't know what universe we're in. I would have to specify some universe. If I would have specified the universe that we're in is all the positive integers, then this would be the set of all integers greater than or equal to 5. Make sense?
Yeah.
So this is the only one that's a little bit weird, set complement. But it turns out it's one of the most useful ones. So just got to get comfortable with it. Okay, so now another thing we talked about last time were relations. A relation is just a set of ordered pairs. F here is a relation, G here is a relation. They're sets of ordered pairs. And then we talked about a function. A function is a special type of relation. A function is a relation where every left-hand element is paired with one and only one right-hand element. So let's look at these two. F is 1 goes to 3, 2 goes to 3, 3 goes to 4, 4 goes to 5. Is this a function?
Yes.
Yes.
Sorry, it is.
Because we don't have 1 goes to 3 and 1 goes to something else. Let's look at the relation G. Is this a function? 1 goes to 3, 2 goes to 4, 3 goes to 5, 1 goes to 6. No, it's not a function because we have 1 goes to 3 and we have 1 goes to 6. Doesn't work. If I would have replaced this 1 with a 4, now is it a function? Yeah, now it's a function. Okay, now we had this notation, F colon A arrow B. We remember how we read this?
F from A to B.
Yeah, F is a function from A to B. If you see F is a function from A to B, you know three things immediately. You know that F is a function, you know that A is the domain of F, or all the left-hand elements, and you know that the image of F, or all the right-hand elements, are a subset of B. Not necessarily equal to B, but a subset of B.
Yeah.
Remember that? So for the F I've drawn here, is F a function from A to B? Here's A, here's B, here's F. Is F a function from A to B?
Yes.
Yeah? What about G? Is G a function from A to B?
Yeah.
Yes.
You good? You seeing how? With F, all the left-hand elements are members of A, and every member of A is a left-hand element. So what's the domain of F? It's a set 1, 2, 3, 4. Is that equal to A? Yes. So we're good so far. Now let's look at all our right-hand elements. 3, 3, 4, 5. Is that a subset of 3, 4, 5, 6? Yes. So its image is a subset of B. So f is a function from A to B. Similarly with G, look at all its left-hand elements, 1, 2, 3, 4, that's equal to A. So it is from A, is it to B? 3, 4, 5, 6, that's equal to B, which is a subset of B. And so yes, it is also a function from A to B. Good? All right, little throwback there. Okay, so the next topic that we're going to cover, and we're just barely briefly going to touch on it, is graph theory. We're just going to do a teeny bit of graph theory just to give you more experience working with different mathematical models before we work our way up to definite, finite, or a finite automaton, which is a 5-part definition. So just trying to work to give you some simpler stuff before we get to the more complex stuff. Okay, so graph theory. All right, definition of a graph. What's a graph? A graph is an ordered pair, a list with 2 elements, an ordered pair. Here's our ordered pair. So our graph G is equal to the ordered pair V comma E, where V is a non-empty finite set, and G is a set of 2-element subsets of V. So V is some set of things. We call V the set of vertices or the set of nodes. And E is a set of 2-element subsets of V. So E is a set of subsets. V is a set of nodes. E is a set of subsets of nodes. And all the sets in E contain exactly 2 elements. And we'll see why here in a sec. So we call V the vertices or the nodes. We call E the edges. And we'll see why here in a sec. So here's an example. G is equal to, here's our V. It just has to be some non-empty finite set. 1, 2, 3, 4, 5.
Does that mean it can't be 0?
The empty set, is what I assume you meant by 0.
Well, it says non-empty and 0 is empty, so does that mean it cannot have 0?
0 is a number. That's an empty set.
Okay, so no.
It can't be this.
Okay, yeah.
I could put the set containing 0. This is a perfectly valid set for V. Okay. So G is equal to, we have some non-empty finite set here. 1, 2, 3, 4, 5, why not? And then E here is a set of 2-element subsets of V. Notice that each one of these are a 2-element set, and each one of these, oops, missing ending my set here, goes and our outer set, then parentheses. Sorry about that. So here's E, start, end. E has 5 things in it. 1, 2, 3, 4, 5. And each of those 5 things in E are a 2-element subset of E. Notice that the set containing 1, 2 is a subset of 1, 2, 3, 4, 5. 2, 3 is a subset of that. 3, 4 is a subset of that. 4, 5 is a subset of that. 5, 1 is a subset of that. Do you see so far how G matches our definition?
In your definition, did you mean on the second part, and G is a set of 2, or and E is a set of 2?
E. G is not a set. G is equal to this ordered pair.
You wrote G.
I did? Thank you. Yep, that's a mistake on my part. Good eye. And E is a set of 2-element subsets of E.
What if V only has 1 element in it? Is that just automatically disqualified because you can have 2-element subsets?
It's okay for E to be empty. So this is a valid graph.
What graphs are we talking about?
We'll connect this now with a picture.
Okay.
And that's
This is a non-empty finite set, and everything in here is a 2-element subset of that.
yeah, I see.
Vacuously satisfying the definition.
Right.
Now you see why understanding this vacuously true thing is so crucial in math. It comes up quite a bit. Okay, so now, why are these things named this way? And why should this definition feel natural to you? And we'll make it feel natural to you now. So, first we're looking at G. I'm going to draw out G here. And I'm going to represent each of the vertices or nodes as just a circle with a label on it. So here I wrote them out, 1, 2, 3, 4, 5. I wrote them in a weird order just because I know where this is going, but There's no compelling reason that I've distributed them that way. You could distribute them however you want. You with me? Okay. Now, so you take each of the vertices, draw them as a label inside some circle. Now, for each one of these two-element subsets, create a line segment connecting those two vertices. So I have the set 1, 2 in here. So create a line segment connecting those two vertices or those two nodes. So there's 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1. So here's a pictorial way of representing the same graph. Here's its definition. Here's a pictorial way of representing it. We call these line segments here the edges, and we call these the nodes. And so you could have just as easily started out with this picture and reconstructed its precise definition.
Oh, that's why you get an MPD, you just don't need line segments.
Right, so an empty, or a graph with just one element, we could do circle 0 like that, and that's a valid graph by itself, just one node sitting there. Valid graph. All right, so here's a graph of G. Let's look at H over here. So H, we have the nodes 1, 2, 3, 4, and the edges 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. So that looks like this. 2 goes to 4, 2 goes to 3, and 3 and 4 are connected. Make sense? So here's some pictorial representation of this graph. I could have given you the exact definition of the graph, or I could have just given you this picture and you would have been able to reconstruct this graph. You could look at this picture and from this picture say, okay, my nodes are 1, 2, 3, and 4. So write a set 1, 2, 3, 4 there. And then let's see, 1's connected to 2, to 3, and to 4. So write those subsets in there. Oh, I missed them. Sorry. I can't believe I did that. Right? Here's V, here's E, start and end. And everything in E is a two-element subset of V. H has to be a list just containing two elements. H is a list containing two elements. This set and this set. Those are the two things in H. Make sense? Okay. Now, that's the notion of a graph. We also have a notion of a directed graph. So a directed graph is an ordered pair, G equal to V comma E, where V is still just a non-empty finite set, same as it was before, but now E is a relation on V. What's a relation? It's a set of ordered pairs, and we say it's a relation on V, we mean that all the ordered pairs are elements of V. So now it's a set of ordered pairs rather than a set of two-element subsets. Right?
Yeah, and the definition between a two-element set and an ordered pair would just be that order matters in an ordered pair.
And duplicates matter.
Okay.
Right? So now I'm going to convert these two really quick to a directed graph. So if I take G, and instead of all these curly braces here, if I were to instead replace it with parentheses like this, now notice that this set right here is a relation, because it's a set of ordered pairs. Furthermore, all the things in the ordered pairs are in V.
So relations are not lists. Relations are not listed in an ordered way, where they don't have to be.
They have. You're saying the fact that 1, 2 came before 2, 3, does that matter? No.
Okay.
If I were to, let's do that. Let's make this a 2, 3, and this a 1, 2, and I didn't change it. So the order inside the set doesn't matter, But if I were to take that 2, 3 and switch it to be a 3, 2, now I changed it. That's something completely different. You with me so far? Now how do we represent this as a picture? By directed, we just give a direction to each edge now. So we say 2 goes to 3. The way we represent that is we, instead of just drawing a line segment, we draw an arrow. 2 goes to 3. And we had 1 goes to 2. So this becomes an arrow. And we had 3 goes to 4. So this becomes an arrow. We had 4 goes to 5. So this becomes an arrow. We had 5 goes to 1. So this becomes an arrow. If I were to come along and switch this from a 1, 2 to a 2, 1, that changes the direction of this arrow. So rather than it going from 1 to 2, that flips this arrow around. So now it's going from 2 to 1. Make sense? So that's a graph. H here is a graph. G here is now a directed graph. Good? All right, let's do a little bit with our example from last time. So last time we talked about rock, paper, scissors, and we wanted to create the beats relation on rock, paper, scissors. You remember doing that? So the way we do that is we create the relation. I'm going to call the relation beats, and it's going to be equal to, our first thing in here is we say rock beats scissors, scissors beats paper, and paper beats rock. So here's our beats relation. And this is a relation on the set rock, paper, scissors. So now I can create a directed graph, G, equal to, our vertices is going to be rock, paper, scissors, and we'll use the beats relation. And now we can construct a directed graph with this thing. And so, for each one of these, we create a little node. Here's our rock node, here's our paper node, here's our scissors node. Now, we know that rock beats scissors, so we have an edge from R to S. Rock beats scissors, scissors beats paper, and paper beats rock. And so, here's some way that we can represent the rules for the game rock, paper, scissors. We can represent it with the directed graph. Good? Okay, so we're going to do one theorem with graph theory, but before that, start with something a little simpler because I think this is the first theorem I'm proving in class. And we'll work our way into it. We'll go back and prove something from set theory, and we're going to prove De Morgan's for sets. I don't know if we called it that before. De Morgan's, in logic, De Morgan's is the fact that not alpha and beta is equal to, not equal to, logically equivalent to, not alpha or not beta, right? Similarly, not alpha or beta is logically equivalent to not alpha and not beta, right? You remember that? So we're going to prove something similar now with sets. Very useful thing to know about sets. The complement of A union B is equal to the complement of A intersect the complement of B. Not A or B is equal to not A and not B. You with me? And similarly, the complement of A intersect B is equal to the complement of A union the complement of B. And ultimately, the way we're going to prove them is to use this fact right here. It's going to come back to that fact, which is why it's still called De Morgan's, but for set theory. And
it's called De Morgan's?
De Morgan's, yeah. Just named after the guy who discovered that. Okay, so we're only going to bother proving this one. This one's almost identical in how you go about proving it. So let's prove this one. So I'm going to prove that the complement of A union B is equal to the complement of A intersect the complement of B. So 1, let A and B be sets in some universe. So that taking the complement makes sense. And is defined. With me so far? Okay. Then, what is the complement of A union B? That is equal to the set of all x such that x is not in A union B. It's a set of everything that's not in A union B, right? But, what does it mean for x to not be in A union B? That's a set of all x such that it is not the case that x is in A union B. Right?
Yep.
Now, what does it mean for x to be in A union B? That means x is in A or x is in B. Right? And now, notice how I have this written. It's a set of all x such that not x is in A or x is in B. Notice x is in A is a proposition. It's true or false. X is in B is a proposition. It's true or false. So we have something that's true or false or something that's true or false. We're ORing together two propositions. And we have a not outside. We know how to distribute a not over the OR of two propositions. It's called De Morgan's. So this, now using De Morgan's, what I wrote over here, which one are we using? This one? Yeah, this one, from here to here, is what I'm doing from this step to this step. Distribute it through. So we have not this, which is right there, and not this, which is right there. With me? So now we got the set of all x such that x is not in A and x is not in B. Well, what does it mean for x to not be in A? That means x is in the complement of A. And what does it mean for x to not be in B? That means x is in the complement of B. Right? So I have it's a set of all x such that x is in the complement of A and x is in the complement of B. By definition, the set of all x such that x is in some set and x is in some other set is what we mean by the intersection. X is in the intersection of those two sets. This is the exact definition of those symbols when we define intersection. Make sense? And you'd see how we prove something like this, right? Very similar steps. You basically just replace all your ORs with ANDs and all your ANDs with ORs. And it'd be the same thing. Okay. Any questions about that theorem? One that'll come up. It's a useful one, so it'll come up a couple times throughout the class. Because it's complementing, it's pretty useful. Okay. One more thing about graphs, and then we'll prove one thing about graphs, and then we'll be done with graph theory. So, one more definition. In a graph G, the degree of a node, of one node, is the number of edges connected to the node. So the degree of 4 here is 2, because there's 2 edges connected to 4. The degree of 1 here is 3, because there's 3 edges connected to 1. Right? Okay, so that's what we mean by a degree. Now, what are we going to prove? We're going to prove that for any graph G, the sum of the degrees of all the nodes is always an even number. So looking at this graph, what's the degree of this node? 3. What's the degree of this node? What's the degree of this node? What's the degree of this node? Add all those 3's up, what do you get? An even number. Notice that, let's erase one of these. So now the degree of this is 2, and the degree of this is 2. Add up all the degrees, what do you get? 10, which is an even number. You're saying it doesn't matter, you can stay up all night trying to come up with some graph. You could not come up with a graph where the sum of the degrees is odd. And we're going to prove that. It makes sense what we're proving?
Yeah.
Okay, so let's prove it. So let G equal to the ordered pair BE be some graph, any graph, I don't care. You stayed up late throughout the night, you claim that you have a graph, I say, okay, here's your graph. I'm going to prove to you that nope, it still has an even number of edges, or an even number of the degree, the sum of the degrees is even. Jeez. Okay, so there's some graph. observe that each edge, little e and big E, is connected to two nodes. Right? Pick any edge, it's always connected to two nodes.
What does little e and big E mean?
Little e is an element in big E. It's an edge. Big E is a set of all edges. Big E is this set right here. Little e is one of the things in there. It could be like this thing, 2, 4. Here's our little e. Something in there. For any little e that you pick, for any element of big E that you pick, that it's going to be an edge, and an edge is always connected to two nodes. Right? So any one edge that you add, not that you add, but any edge that you have in your graph, say how I have to have it set here. And so, I have to restart. Observe that each edge, little e and big E, is connected to two nodes, and so contributes 2 to the sum of the degrees. Right? So let little n be the number of, be the size of E, the number of edges that you have. Well, little n be the size of E, then the sum of the degrees is equal to 2n, which is an even number. Make sense? So that was a little bit working with graphs, get you familiar with some other mathematical object, doing a couple proofs with it. We don't really need a lot of graph theory in this class. We'll just be working with things that look a lot like graphs, so graph theory is a pretty natural choice. Okay, so now we're going to switch to talking about a completely different topic that was completely standalone. So the next topic that we're going to talk about is induction. And in particularly, we're going to be talking about proof by induction. Now, have you ever seen proof by induction before? Have you? Not sure? All right. Well, we got someone new for it, so we'll make sure we flesh out completely. And then sigma notation. I don't know, is sigma notation? Never seen? Okay, so I figured we probably need to go over that as well. So we can quickly go over sigma notation. It looks dense, but it's a really simple idea. Why do we call it sigma notation? Because the name of that Greek letter right there is sigma. So that's a capital sigma, so sigma notation. Sigma notation is a really dense way of representing a sum of numbers, as in arithmetic, just a sum. So when we say that you have sigma, you have k equals 1 down there, doesn't have to be k, some dummy variable, and some starting number, like 1 down there, and then some other number called n up here, and then some expression with a k in it, then it's going to be equal to whatever that expression gives you when you replace your k with 1, your starting number, plus whatever that expression gives you when you replace your k with 2, plus whatever that expression gives you when you replace your k with 3, etc., until you've replaced your k with n. That's your last term. So that was said a lot there. Let's write some out, and then I think you'll get the definition because it's pretty simple. So we're going to do, and I'll tell you how we read this. Here's the way that we read this. The sum from k equals 1 to 5 of k, and it will make sense here in a second. You'll get used to this language. The sum from k equals 1 to 5 of k is equal to, so here's our expression that has a k in it. First we replace all our k's with the number 1, then we replace all our k's with the next number after 1, which is 2, plus replace all our k's with the next number after 2, which is 3, plus replace all our k's with the next number after 3, which is 4, plus replace all our k's with the next number after 4, which is 5, and then stop because we got to 5. So you stop when you reach whatever that top number is. So looking back at our definition, you do k equals some starting number 1 to some ending number n. It's going to be a sub 1 plus a sub 2 all the way up to a sub n.
Does it do steps?
So in this case, it's 15. So this was another way of writing the number 15. It's just that sum. All right. let's do a slightly more complex one. So I'm going to do the sum from k equals 0 to 6 of 2k plus 1. So when we plug in 0 into, when we replace k with 0 in this expression, what do we get? Plus when we replace it with 1, we get, when we replace it with 2, when we replace it with 3, when we replace it with 4, when we replace it with 5, and when we replace it with 6. And when you add all that up, is that 49? Okay, so that was another way of writing 49. Okay, let's do this one. We're doing the sum from k equals 1 to n of k squared. Notice that we didn't specify some ending number here, n. So the only way we can write this out is it's 1 plus 4 plus 9 plus ... plus n squared, whatever we're ending at. Make sense? Okay, so that's sigma notation. When we do proofs by induction, it's easiest to do proofs with sums. So mostly we're just explaining that to help you understand proof by induction. Okay, how does proof by induction work? Here's the intuition. Imagine that I give you some mystery set. So I have some mystery set A here. And I'm not going to tell you what's in A. I'm just going to tell you two things about A. So A is equal to, you don't know what's in here, you're trying to figure it out. Now I'm going to give you two pieces of information. I tell you first of all that 0 is in A. So you know that much. So you know at least 0 is in there. So this is the first thing I tell you. The second thing I tell you that is if k is in A, that implies k plus 1 is in A. So if you know 10's in A, then you know 11's in A. If you know 50's in A, then you know 51's in A. Anytime k is in A, k plus 1 is also in A. Those are the two things I tell you. So what do you know about A?
It's 0, 1, 2, 3.
Right. So you knew that 0's in there, then you came down here and you said, well, if I know 0's in there, that implies 0 plus 1 has to be in there, which is 1. And now since you know 1's in there, 1 being in there implies 1 plus 1 in there, which is 2. And then 3, etc., 4, 5, ... right? Which is equal to the natural numbers. Okay, that's what we mean by an inductive set. So the set A is equal to the natural numbers, provided that two things are satisfied. 1, the element 0 is in A, and 2, if k is in A, then k plus 1 is also in A. If you satisfy those two conditions, then A is actually equal to the set of natural numbers.
Is that the definition of induction or just an example?
It's almost the definition of an inductive set.
Okay.
But you have the idea. Now, we don't always have to use the entire set of natural numbers. Suppose instead, let's restart this process, and I told you 1 is in A and this. Then what do you know about what's in A?
Then it's 1, 2, 3. And
Right.
so
1, 2, 3, 4, etc. And so then you know that A is equal to all the positive integers. Sorry, you haven't seen that notation before, have you?
No.
This is a set of all integers.
Yeah.
And when we say we just want to talk about the positive ones, we put a little plus sign up there. And if we want just negative ones, we put a minus sign up there. Common notation. Okay, now I lied a little bit. I said A is equal to that set. You don't really know that. You just know that A is a subset, or that this is a subset of A. You just know that Z plus is a subset of A. Because maybe A also has pi in it. You don't know. All you know is this for sure about A and this for sure about A.
Oh, yeah.
A could have other things in there,
Yeah.
but it at least has these things in there. So that's really a subset of A, or the natural numbers are a subset of A, not equal to. But if you just think equals to, you'll be fine with your intuition. But to be technically correct, it's not really equals to. Okay, so that's the big idea of induction. So how do we do a proof by induction? We do a proof by induction when we want to prove that some statement is true for any natural number. And let's jump ahead and give you an example, then read proof by induction. So I might want to prove that for any natural number in n, 11 to the power of n minus 6 is divisible by 5. Let's test that. Pick a natural number really quick.
Little n is natural number.
Yeah. For all little n in big N is a set of natural numbers. So for all elements of the natural numbers, 11 to that element minus 6 is divisible by 5. So pick any element in the natural numbers. 5. Let's pick 2. So that way you can do the arithmetic in our heads. So 2 is a member of the natural numbers. So if we take 11 to the power of 2 and then we minus 6 from it, we're saying that's divisible by 5. Let's see, what's 11 squared? 121 minus 6 is 115, which is a multiple of 5. Because it's equal to 23 times 5. If you can write some number times 5 or some integer times 5, then it's multiple of 5, right? Okay, so here we have some statement that we want to prove, but we want to prove that for every natural number, not just for 2. We want to prove it for 3, for 4, for 5, for 6. How can we do this? We don't just want to test it 100 times. That's taking forever. And even if you test it 100 times, that doesn't prove a statement is true, right? And so proof by induction is how we handle statements like this. So notice that if I represent this as a proposition, I'll represent it as a proposition Pn. Pn is equal to the proposition 11 to the n minus 6 is equal to, and I'll just write it in words here, a multiple of 5. Okay? Sorry. Pn is equal to, we'll put our quotation marks like this. Not proposition, predicate. My goodness. This is a predicate. You can't determine whether it's true or false until you know what your n is.
Yeah.
Once I give you an n, it's a proposition, and then you can determine whether or not this is true or false. So here is some predicate. We want to prove that some predicate is true for any natural number that you plug in. And we use induction to prove that. So here's how proof by induction works. Let P be some predicate, like this.
Yeah.
Let P be some predicate. If P of 0, in other words, P is true for 0, and if P being true for K implies P is true for K plus 1, then P is true for all little n in big N.
What about, oh yeah.
Does that make sense?
Yeah.
So if P is true for 0, and anytime P is true for K, and then P is true for K plus 1, then P is true for every natural number. Or then, for all natural numbers, P of n is true. Make sense? So, that's what we mean by a proof by induction. This exact thing here. So now let's do some examples of this. So, we'll do each of these examples. Proof that for all n in the natural numbers, for every natural number, which one are we doing first? The sum? The sum from I equals 0 to n of I is equal to n times n plus 1 divided by 2. Let's make sense out of what that's saying before we prove it. So we'll test an example. Pick some n. 3. So what this is saying is that the sum from I equals 0 to 3 of I, which is equal to 1 plus 2, well, 0 plus 1 plus 2 plus 3, right? 0 plus 1 plus 2 plus 3.
Oh, you're not going for the imaginary number is I.
No, I is a dummy variable.
Okay.
I is a dummy variable. And we didn't use k because we're going to use k in our proofs for this condition right here. So I picked some other dumb variable, I, and it's a very common one to do. I don't know why I keep curving it the other way, I. So you don't think it's a j. All right, so the sum from I equals 0 to 3 of I is equal to 0 plus 1 plus 2 plus 3, right? Which is equal to 6, which, let's see, is that equal to n times n plus 1 over 2? In our case, n was 3, so is that equal to 3 times 3 plus 1, which is 4, over 2? Yeah, and it worked. All right, let's pretend that this was instead like a 5. So we have plus 3, plus 4, plus 5. So that's equal to 15. Is that equal to 5 times 5 plus 1, 6 over 2? 30 divided by 2, 15. Looks like it's working. So that's what this statement says, except for we're proving it for any natural number you can think of. So we're proving it for an infinite number of cases. All right, so let's prove it. Sum 1. Let A equal the set of all n in the natural numbers such that, I'll only write this out completely explicitly once, such that the sum from I equals 0 to n of I is equal to n times n plus 1 over 2. Or in other words, A is equal to the set of all natural numbers that satisfy that condition. My goal is to prove that A is equal to all the natural numbers. And then we're done. A is everything that makes a statement true. If I show that A is equal to all the natural numbers, then all the natural numbers make that statement true. That's a big picture of what we're going for. That makes sense? Okay, so let A be the set of all the natural numbers that make the statement true. What do I need to prove about A? I need to prove two things. First, I need to show that 0 is in A. And then I need to show that if K is in A, then K plus 1 is also in A. And if I can show those two things about A, then A is equal to all natural numbers. That makes sense? Okay, so 2. Observe that the sum from j equals 0 to the 0 of j, not j, I equals 0 to 0 of I is equal to 0 is equal to 0 times 1 over 2. Right?
Doesn't 1 go to 0 since 0 is the starting?
We're summing all the numbers from 0 to 0 of 0.
Oh.
Right? So notice that when we plug in 0 for n, the statement's true. Right? We have the sum from j equals 0 to 0 is equal to 0 times 0 plus 1 over 2. Comma. And so we know that 0 is an A. A is a set of all natural numbers that make the statement true. We just showed that 0 makes the statement true. Good? So now I want to show if K makes a statement true, then K plus 1 also makes a statement true. So 3. Let K be any element of A, anything that makes a statement true. Since K is in A, then that means, let K in A, comma, so that means that the sum from I equals 0 to K of I is equal to K times K plus 1 all over 2. A is a set of all the natural numbers that make this statement true. K is some random element in A. So K has to make the statement true. You follow that? Good? Okay.
So why don't we have any numbers for the formula? Before k times k plus 1 over 2.
Well, we what?
Why don't we have any numbers before k times k plus 1 equals 2?
Any numbers?
Like the list that we usually do. How it goes from 0 to 1 to 2 to 3 to 4.
Oh, so far we proved zeros in there, right?
Yes.
So we are dealing with some secret set A. We don't know what A is. We know that A is a set of all the natural numbers that make the statement true, but we don't know which natural numbers that is. We explicitly showed that zeros in A, so we at least know that. Now the second part of the proof is to show that if k is some random element in A, then k plus 1 is also in A. If I can show this, then that means now we know what A is.
Well, A could be a subset.
Well, we said A is going to be the set of all natural numbers that make the statement true. So we already know that A is a subset of natural numbers. The second part is to show that natural numbers are a subset of A, therefore they're equal. But that's just a detail. So we already showed that 0 is in A. Now I need to show this part. If I can show that anytime k is in A, k plus 1 is also in A, then we now know that A must also contain 1 and 2 and 3, etc. You with me? So we showed zeros in there. So I'm saying pick any random thing in A. Call it k. K could be 0. So far, all we know in there for sure is 0. So you can think about it as being 0 right now. And I'm going to use the fact that 0's in there to show that 1's in there. And the same method I do that with, you can use to show, now that we know 1's in there, we can show 2's in there, etc. So let k be any random element in A. So I know that k makes a statement true. When I replace my n's with k, the statement's still true. Right? Okay, then the sum from I equals 0 to k plus 1 of I is equal to, what is this? This is 0 plus 1 plus 2 plus 3 plus 4 plus 5, all the way up to plus k plus 1. Right? So this is equal to the sum from I equals 0 to k of I. So 0 plus 1 plus 2 plus 3 all the way up to k, and then plus k plus 1. Let's pick a concrete number for a sec to make sure this makes sense. Let's pretend that k was 5. So then this right here is shorthand for 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. Which is the same thing as 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6.
Yeah.
Okay, so we just took the last element out there and wrote it separately. With me?
Yeah.
Okay. Now this is equal to, we already know what the sum from j equals 0, or from I equals 0 to k is. We know that's equal to k times k plus 1 over 2. We know that this is equal to this. So then this is equal to k times k plus 1 over 2 plus k plus 1. Follow that? Which is equal to, I'm going to get a common denominator, so I'm going to take this term and multiply it. I'm going to treat this all like one term, so parentheses there. And I'm going to multiply top and bottom by 2. So rewriting this, that's k times k plus 1 all over 2, plus multiply this top and bottom by 2. So that's 2k plus 1 divided by 2. You with me? And notice that that and that have a common denominator, so we can rewrite that all as one fraction. This is k times k plus 1 plus 2 times k plus 1 all over 2. You with me? Okay, now I can factor a k plus 1 out of both these terms. So this is equal to, factor the k plus 1 out of both these terms, we get k plus 1 times, when we factor a k plus 1 out of this term, we're left with k. And when we factor a k plus 1 out of this term, we're left with 2. All over 2. You follow the algebra?
Yeah.
Okay. Notice what we just showed. We just already showed that the sum from I equals 0 to k plus 1 is equal to k plus 1 times k plus 1 plus 1 over 2. Or in other words, it fit this formula. We got k plus 1 times k plus 1 plus 1 all over 2. So k plus 1 satisfies this statement, whatever the number is. So since that, so k plus 1 is in A.
So you couldn't take that k times k plus 1 over 2 plus k plus 1 and make it work. Or you couldn't plug in a number and it wouldn't come out right.
I'm not sure I understand what you mean.
With that one on the furthest right on top of number 4.
Yes?
This one, yeah, that one. You couldn't plug in I did 7 and get it to come out 8. Yeah, you can at the bottom one. So it changed.
Here's what we just did. So up here we showed 0 makes a statement true. Okay, now imagine that k is 0. You with me? So k is 0. So we just barely showed that the sum from I equals 0 to 0 is equal to this, right? So then the sum from I equals 0 all the way up to 1 is equal to the sum up to 0 plus 0 plus 1, or 1. Right? Which is equal to 0 plus 1, which is equal to 0 plus 1, which is equal to 0 plus 2 divided by 2, which is equal to 1 times 2 divided by 2. So still 1, right? So now we just really showed, okay, so 1's in there. Now restart, this time k is equal to 1.
It only works if k equals 0.
No, because now think about k equal to 1. So we showed it works for k equal to 1. We've now shown that 1 is in A. So we knew 0 is in A, we used that to show 1's in A. Okay, so now restart thinking about k as being 1. So, so we know, let 1 in A. Pretend that k is equal to 1. So we have now shown that the sum from I equals 0 to 1 is equal to 1 times 2 divided by 2. Right? Alright. So then the sum from I equals 0 to 2 is equal to the sum from I equals 0 to 1 plus 2. Which is equal to 1 times 2 over 2 plus 2 and that's going to be the same thing. The algebra still works out the same. And so it's equal to this. So it's going to end up equaling 2 times 3 over 2. 6 divided by 2 is 3. This was 1 plus 2.
So we were at 1. So we're going from 1 proves 2. And then proves
We showed that 1 was in there. Now we're showing that 2's in there.
We came out with 3 though.
Right. That's what this formula says. This formula says if you add up all the numbers from 0 to 2, you should get 2 times 3 over 2, which is 3. And it came out to 3.
Okay.
So now we know 2's in there. We know when you add up all the numbers from 1 to 2.
How does that prove 2 if we got 3?
we showed that 1 plus 2 is equal to 3. Or is equal to 2 times 3 divided by 2, which is 3. That's what we proved.
So we're using a number we don't know in there to prove that a different number is in there.
We're using the fact that we knew 1 was in there to show that 2's in there. So now we know that 2 satisfies this statement, right? I still think you're overthinking it.
I'm confused where we got 3 from. How are we using 3 if we don't know it's an A?
No, we showed that the sum of the numbers from 1 to 2, or sorry, the sum of the numbers from 0 to 2, maybe put my 0 here to make it clear. The sum of the numbers from 0 to 2 is equal to 2 times 2 plus 1 over 2, which is 3.
Yeah.
Right? So now we know that 2 is in A.
Because it worked.
2 is one of the numbers that we can replace n with to make the statement true. If I replace all those n's with 2, the statement's true.
Yeah.
Okay, what about if I replace them with 3? Is the statement still true? How do you know? You go through this exact process again. We know 2's in A. So we know that the sum from 0 to 2 is equal to 2 times 2 plus 1 over 2. Right? So then, the sum from 0 to 3 is equal to the sum from 0 to 2 plus 3. Which is equal to the sum from 0 to 2 plus 3. Just do the algebra. And it's going to come out equal to, what was our k? 2?
2.
So it's going to equal to 3 times 4 over 2. 3 times 4 is 12, divided by 2 is 6.
Okay, yeah.
So now we know 3's in there. Okay, now we know that 3's in there, how do we show 4's in there? Same way. And then how do we show 5's in there? Same way. And you can do that an infinite number of times to show that every natural number is in there. So we showed 2 things. We showed some starting numbers in there. We showed that 0 was an A. And then we showed k in A implies k plus 1 is an A. Because we never required k to be any specific number in all this algebra. We said k could be any number you want. So when you plug in 0, when you start with 0's an A, we show 0 plus 1's an A. When you start with 1's an A, we show 1 plus 1's an A, or 2's an A. When you know that 2's an A, we show 3's an A. When you know 3's an A, we show 4's an A. We showed anytime k is a number in A, k plus 1 is also an A. That's the way the proof works. So k plus 1's an A. 5. Therefore, A is equal to the set of all natural numbers. Make sense? Maybe take it one step further to make sure you're clear why that matters. We showed A is equal to the set of all natural numbers. A was a set of all the numbers that made the statement true. So maybe write one more line. 6, therefore, comma, for any natural number in the natural numbers, then the sum from I equals 0 to n of I is equal to n times n plus 1 over 2. And that's what we showed. Does that make sense? All right, let's do another one. So this time, we're going to do the divisible by 5 one.
Is there a way to write that in like numbers or symbols or something?
Yeah. Let's specify that for a second. 5 divides n is what we mean by n is divisible by 5. It's just a vertical line. And that's logically equivalent to there exists some integer k such that n is equal to 5k. So to say that 5 divides n, or n is divisible by 5, means that there exists some integer called k, such that n is equal to 5k, or n is some multiple of 5. And that's its precise definition.
Okay.
Okay. So, we want to prove that for any natural number, for all natural numbers, comma, 11 to the n minus 6, let's just write it out with our notation. 5 divides 11 to the n minus 6, and then put parentheses there to specify what 5 divides. You with me? Okay. 1. Let A equal the set of all natural numbers, all n and big N, such that our statement up here is true. We won't bother writing it out, right? It's a set of all the natural numbers that make the statement true. So if 10 makes the statement true, 10's in this set. If 11 doesn't, 11's not in the set. We're going to prove that every natural number is in the set A. Good? All right, 2. So first let's show that 0's in there. Observe that 11 to the 0 minus 6 is equal to, what's 11 to the 0? 1. Anything to the power of 0 is 1. Might remember that from algebra. Minus 6 is equal to, 1 minus 6 is negative 5, is equal to negative 1 times 5. Some integer times 5. So this was a multiple of 5. So 5 divides it. So 0 must be in A. Because 0 makes the statement true. And A is a set of all the numbers that make the statement true. Good? Alright. The weird part. 3. Not assume. Well, I'll get to that in a second, but let's be very explicit about these proofs for a bit. 3. Let K be any element in A. So far, we only know 0's in there. But we're going to do this in a very generic way, so that when we know 1's in there, K could also be 1. And when 2's in there, K could also be 2. So we're doing it in a very generic way. So let K be any element in A, comma. So we know that 11 to the K minus 6. So we know that 5 divides 11 to the K minus 6. Whatever K is. If K is in A, K has to make the statement true. Maybe put parentheses there. Right?
Okay.
4. So then, maybe make this very clear. Let K in A, so 5 divides 11 to the K minus 6, comma, or there exists some integer m such that 11 to the K minus 6 is equal to 5 times n. If 5 divides 11 to the K minus 6, that means there is some integer, we're going to call it m, such that 5 times m equals 11K minus 6. Where 11 to the K minus 6 has to be some multiple of 5, since it's 5 divides it.
So you have to introduce n in your proof while you're writing this down?
I did.
Where's that? How are you going to introduce it?
Yeah.
You
Since
have
we know that 5 divides this, then we know that there must exist some integer m such that that's the case. Make sense?
Yeah.
Okay, 4. Then 11 to the K plus 1 minus 6 How am I going to want to do this? I'm missing something obvious. You see how to go with it? Oh. Make one more note just with the algebra here, because I don't want to lose you in the algebra. So there exists some m such that 11 to the k minus 6 is equal to 5m, or another way we can say that is 11 to the k is equal to 5 times m plus 6. You with me? Okay. So 4. Then, now we're trying to show that k plus 1 makes a statement true. Or in other words, 11 to the k plus 1 minus 6 is a multiple of 5. So then, 11 to the k plus 1 minus 6, what does that equal to? Well, 11 to the k plus 1 is the same thing as 11 times 11 to the k minus 6. Right? Everyone good with that algebra there with exponents?
Yeah.
Because we can think about that as 11 to the 1. When you multiply terms, you add the exponents. Okay, but now I know that 11 to the k is 5 times m plus 6, where m is some integer. So I know that at least 11 to the k can be represented this way. So this is equal to 11 times 11 to the k can be represented as 5 times some integer, we don't know what, but some integer, plus 6. And then we have minus 6. Right? Which is equal to, do the algebra here, we have 11 times 5m, so that's going to be 55m. Maybe I'll just leave that as 11 times 5m. 11 times 5m. That should be there. Now 11 times 6 is,
6.
minus 6 is, so plus 60. Right? Which is equal to, I'm going to write my 5 first here. 5 times 11 times m plus, and rather than writing that as 60, I'm going to write that as 5 times 12. Factor out the 5, so it's equal to 5 times 11 times m plus 12. Or 5 times some integer, some number. What one? Who cares? 11 times some integer is still some integer. When you plus 12 to it, it's still some integer. And so, 11 to the k plus 1 minus 6 is equal to 5 times some integer. Comma. And so, k plus 1 is also an a. 5, therefore, a is equal to set of all natural numbers. And let's walk through this one more time with an example. Let's pretend that you already worked it out for the case of n equal to 10 and you found out it's true. Okay? Let's say you personally tested 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 is the last one you tested. I'm going to show you how this method automatically gives us 11 for free. And then when you know 11, it automatically gives you 12 for free. So let's see that really quick with the math. So you already tested it, and you know that 11 to the 10 minus 6 is equal to 5 times some number. n. We don't know. n. Whatever it is. Right? Well, I don't know if spelling it out like that does anything for you. So then 11 to the 11 minus 6 is equal to 11 times 11 to the 10 minus 6, you already found out that 11 to the 10 minus 6 is equal to this, or in other words, 11 to the 10 is equal to this. And so I just use that in my substitution here. I say you already found out that when you put a 10 there, you get this number. So I take 11 times whatever number you got, minus 6. Again, we can rewrite it like this. We can rewrite it like that. We can rewrite it like that. And so we show the 11's in there. Make sense? How these are kind of just recursive. Therefore, a is equal to n. Therefore, every natural number makes the statement true. And we're done. And that's why we love proof by induction. We're able to prove an infinite number of cases all in one go. Pretty crazy. Any questions about that one? You think you got it? Should we do some more? Want to see another one?
I got it.
You got it? Another one? One more? You like one of those more than the other?
Yeah, the bottom one.
You like the bottom one more than the top?
Yeah.
I think this one's more interesting because it says something cool.
That's why it's more complicated.
Because this one says, if you sum up the first n odd numbers, it's equal to n squared. In other words, if you add up the first 5 odd numbers, it's 25. If you add up the first 100 odd numbers, it's 10,000. So that's why this one's kind of cool.
Oh, I see.
This one is more complicated, but it's just not as interesting. So now that I showed you why that one's cool, you want the top one or the more complicated one?
Either or.
You don't care? This one also I did from 1 to n instead of 0 to n, just to show a different starting point. So we'll do this one. Right, so we're going to prove for all natural numbers, not for all n this time. For all positive integers. For all n in z plus all positive integers, then the sum from I equals 1 to n of 2I minus 1 is equal to n squared. So let's understand this statement really quick. Let's pick a number for n. 4. So let's write this out. This is just get comfortable with the sigma notation. So we're doing I equals 1 to 4 of 2I minus 1. When we plug in 1 for I, that's 2. 2 minus 1 is 1. Plus, when we plug in 2 for I, 4 minus 1 is 3. Plus 5 plus 7, right? 7 plus 5 is 12, plus 3 is 15, plus 1 is 16, which is equal to 4 squared. Right? Okay. So, cool fact. Sum of any number of odd numbers, and it's equal to that number squared. Let's prove it. All right. And notice that we're proving something a little bit different now. What am I showing? First, I'm going to show that 1 is in A, and then I'm going to show if k is in A. That implies k plus 1 is in A. So now our starting point is at 1. And so now we're going to know 1's in there, and since 1's in there, 2's in there, since 2's in there, 3's in there, etc. Right? Okay. So 1. Let A equal the set of all the positive integers such that that is true. Right? 2. Observe that the sum from I equals 1 to 1 of 2I minus 1 is equal to, when we replace the I with the 1, we get 2 minus 1 is 1, is equal to 1 squared. Right?
Mhm.
Which implies that 1 is in A. So we know 1's in A. And I may get lazy in my proofs. I'm going to start using arrows a lot in my proof. When I put an arrow in my proof, I mean the last thing we said implies the next thing I write. Because get really lazy writing out all these wordy proofs. Okay. Let K be any element in A. Well, if K is in A, what does that mean? That implies that the sum from I equals 1 to K of 2I minus 1 is equal to K squared. Right? So, then the sum from I equals 1 to K plus 1 of 2I minus 1 is equal to the sum from I equals 1 to K of 2I minus 1 plus whatever we get when we plug in K plus 1 for I here. So maybe I'll write this real explicit so that we see all the algebra. This is the sum for when you plug in 1, plus when you plug in 2, plus when you plug in 3, plus dot, 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 plus when you plug in K, plus when you plug in K plus 1. Right? That's what this is. It's equal to the sum when you plug in 1, plus when you plug in 2, plus when you plug in 3, plus when you plug in dot, 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 plus when you plug in K, plus when you plug in K plus 1.
Okay.
You follow that? Okay. Now we know what you get when you take the sum from 1 to K. You get K squared. So this piece is equal to K squared. So that's equal to K squared plus this. Now let's figure out what this equals. Yeah, let's figure out what it equals. So when we distribute the 2 through, we're going to get 2K plus 2 minus 1 is going to be 2K plus 1. You follow that? Okay. Which is equal to, now we got to factor this in.
Where did we get K squared?
This is equal to K squared.
Oh, okay.
And then 2K plus 1 is this thing.
Yeah.
Now notice that K squared plus 2K plus 1 is exactly K plus 1 squared. K times K is K squared. K times 1 and 1 times K gives us 2K. 1 times 1 is 1. So that gives us that K plus 1 is in A. And so A is equal to all the natural numbers. And so it's true for all the natural numbers. Or for all the positive integers, I mean. Right? Good?
Yeah.
Okay. Think you need to see the last one, or you think you're good? Think we're good? Good?
Yeah.
All right. I know proof by induction, it's a bit to take in the first time you see it, but it's also one of those things that once you get comfortable with it, it's like the first way you think to try and prove something if you can. You learn to love it. It seems super complicated, and then you learn to love it because it's kind of the same formula no matter what you're doing. And so it makes your proofs actually pretty easy when you can't use proof by induction. So, complicated the first time you see it, but if you continue in maths, you'll learn to love proof by induction. It's going to be your go-to anytime you can. All right. Okay. So thus far now, we pretty much finished all the preliminary stuff for the class. And now we're jumping into computation theory stuff. Okay? So switching gears, that was everything we've done up till now. That was just preliminary stuff that you most likely would have come across in previous math classes prior to this.
So computation theory is basically a coding language.
What? A coding language?
Coding, understanding what computers do.
It is understanding what computers do. Yeah, it's hard to get intuition for it until you just jump in. All right, so we'll jump in. Some terminology that we gotta get comfortable with now for talking about from here on out. One, so talk about strings and languages. I told you that for some reason should no way appeal to your intuition right now, but for some reason talking about languages and talking about models of computation seem to be somehow logically equivalent, which seems weird, seems completely unintuitive. You'll get used to that as the class goes on, but it is just the case. And so we use similar languages when talking about computation theory and when talking about languages. So you just gotta get used to this language here. So here's some terms that we're gonna use a lot. Let's get used to them. An alphabet. What's an alphabet? An alphabet is a non-empty finite set. That's it. An alphabet is a non-empty finite set. Examples of alphabets. Typically, we use sigma to represent alphabets. This has nothing to do with that summation notation over there. It's just that the same symbols show up in different places. The same way that sometimes that symbol means multiply, sometimes it means the letter X.
And it's called the same thing.
So, yeah, because that's the name of the Greek letter. The name of it, sigma.
Okay.
So, yeah, nothing to do with summation notation, just sigma. We typically use sigmas to represent alphabets, just common notation. So I might say sigma sub 1 is the alphabet that we all know and love, A, B, C, D, E, F, G, all the way up to Z. Another alphabet that we'll be using a lot in this class, sigma 2, is equal to just 0, 1. We call this a binary alphabet.
Is this like sigma 1, sigma 2 thing like a general thing that's used throughout computation theory?
The same way that n typically represents a natural number or a positive integer, sigma, in the context of computation theory, typically represents
Right, but I mean,
alphabet.
does sigma sub 1 actually mean?
Oh, no. These aren't definitions.
Oh, okay.
I'm just picking different variable names.
Okay.
Right? So you might see it come up, sigma 1 equal to that. Sigma 2, here's one that we'll use a lot. I see what you thought, because of 2 there. Sigma 2, this alphabet in particular we call the binary alphabet. Anytime you hear me talk about the binary alphabet, it's 0, 1. If you know how computers use binary, that's because they use 0, 1s. So we'll use this one a lot. Another alphabet we'll use a lot is just A, B. So here's another possible alphabet. And then if we get tired of using sigmas and we need another letter, like sometimes you get tired of using n's for natural numbers, so you sometimes use the letter M. Well, we also have capital gamma in the Greek alphabet that we sometimes use to represent alphabets. Gamma, that's capital gamma.
How's that different from T?
It's weird.
It's kind of like a upside down L.
So one side is supposed to be longer.
So one side's supposed to be longer,
And then tips at the end.
and then there's a lot of different ways to write it. If you just watch a Greek person writing, they just draw like this. If they're just writing along. To help it make it more clear from our context, I'll try and make it stand out a little.
So is sigma 3 a subset of sigma 1?
This happens to be a subset of that. These are not sigmas we'll be using throughout the whole class. And I'm just coming up with random examples and naming them. It's just a random alphabet. You can have an alphabet with A, B in it. You can have 1, 2, X, Y. That's a valid alphabet.
Why?
Alphabet's just a non-empty set.
Never mind.
Non-empty finite set. Okay. Symbol. What do we mean by a symbol? Let A be an alphabet, then any member of A is called a symbol. So we call that the symbol A, the symbol B, the symbol C, the symbol 0, the symbol 1, etc. If I say consider the symbol, you instantly know it's a member of an alphabet. It came out of some alphabet.
But sigma is a symbol, so that came out of an alphabet.
No, this is not the symbol in this context. That's the name of our alphabet. That's the name of this alphabet. A symbol is a member of an alphabet. So the symbols of the English language are A, B, C, D, E, F, G, etc. Those are different symbols. Now the strings, which you can kind of think about like the words, a string is a finite sequence or list of symbols.
So it's the alphabet?
No, you take a bunch of letters from your alphabet and put them in some order. And you have what we call a string. So, hello, from the English language,
Is it a string?
is a string. That's a symbol, that's a symbol. Now, if we were to write it out completely properly, we'd write H, comma, E, L, L, O. That's how we write out the word hello properly. That's kind of tedious, and so we just write like this, and it's implied that you understand. Now, we're writing those in a particular order, and there's exactly 5 symbols. Okay, so string, a finite sequence or list of symbols. So if our alphabet were the letters 0, 1, or the symbol 0, 1, then a string generated from that alphabet might be 1, 1, 1, 0, 1, 0. Now, this is super tedious, and I'm never going to write our strings this way. Instead, we're just going to write W is equal to 1, 1, 1, 0, 1, 0. Now, it is understood from context that this is not the number 111,010. It's just a string. It's just a word generated with this alphabet. It's shorthand for this list. This list is not that number. Those are 2 different things. Make sense?
Is there any way to like show it differently, or is that?
This is the way we're going to write it from here on out. We will hardly ever be doing any arithmetic in this class. So when we're writing out numbers like this, it's almost guaranteed that we're talking about them as symbols.
Okay, yeah.
And we'll do strings like this all the time. So that string will never mean, unless I specifically tell you. I'll specifically tell you when I mean it to mean a number. I don't know if I'll ever mean it to mean a number. But I guess it's possible. Okay, so don't let that get you. String length is the length of a string, W, is the number of symbols in the string. What's the length of this string? 6, because there's 6 symbols in there. And we write that as kind of like the absolute value of the string. This is shorthand for the length of the string.
So it's not the same thing.
It's not the same thing as absolute value, because absolute value takes a number. That's just our length symbol. And it's just using that same absolute value symbol. A lot of repeating symbols with different meanings. Okay, finally, what's a language? A language is a set of strings. If we were to take English, the English language, take all the words in the dictionary, and throw them together in a set, that's the English language. It's the set of all the English words, or all the English strings. Take all our valid strings generated from our alphabet. That's the English language. Good? And then finally, we have the notion of an empty string, which we'll represent with this epsilon, Greek letter epsilon. This is shorthand for the empty string, the empty list, no symbols. The same way that we have the empty set is equal to this, the empty list is equal to this. Different ideas, different concepts. The empty string is still a string. This is not a string. Good? Okay. All right. So let's now design our first computer. And here's the problem. So your job is to design a computer for some store owner. So some store owner, here's the store, here's the front door to the store. With me? The door swings open this way. So it's not a slide open door, it's a swinging door. You are designing for the store owner some computer, some mechanism to automatically open and close the door for people. The input information coming to you is there's a front pad here and a back pad here, And the input information you have is whether or not someone is standing on that pad. Make sense? So you have two streams of information coming into your computer. One telling you whether or not someone's on the front pad, and another one telling you whether or not someone's on the back pad. So there's 4 possible sources of information. You can get just someone's on the front pad, or just someone's on the back pad, or there's someone on each, or there's no one on either.
Wouldn't you open it no matter what?
If there's someone on the back pad and you just open it, you'd whack them. You don't want that.
So no one's allowed out of the store?
Oh, someone can open the door handle by hand.
Oh, okay.
Yeah. So someone can open the door by hand, but the store owner wants the door to be open as much as possible when people need.
Okay.
Wants to help out as much as possible
Right.
with some machine. But yeah, people can just open the door and walk out if they want. Yes. It's just a mechanism for automatically doing it, to save some people the hassle. And obviously we don't want to automatically open the door if someone's staying on the back pad, otherwise we'd whack them.
Right.
Right? So before we design our little state machine for this, let's first think about all the possible cases. So all the possible states that our door can be in is it can either be open or it can be closed. Those are all the possible states the door can be in. All the possible inputs the door can receive, our computer can receive, is there's someone on the front pad, or there's someone on the back pad, or there's someone on both, or there's someone on either. So these are all the possible inputs we can receive to our computer, and these are all the states we need to keep track of in our computer. You with me? Our job is to calculate what state should we change the door to, depending on what input we receive. So, for example, if the door is already open and someone is standing on the front pad, what do we want to do?
Stay open.
We want the door to stay open. So in that case, we want to stay in the state open. If the door is open and there's someone only on the back pad, what do we want to do?
Stay open.
Stay open,
Oh, okay.
right? Because they might be trying to walk out.
Right.
If the door is already open and there's someone on both the front and the back, what do we want to do? We want to keep the door open. Finally, if the door is open and there's nobody on the front or the back, what do we want to do? We want to close the door. Similarly, if the door is closed and there's just someone on the front pad, what do we want to do? We want to open it. If the door is closed and there's just someone on the back pad, what do we want to do?
Keep it closed.
Keep it closed.
There's some people you want it to be open for.
Right, but we don't want to try and help some people at risk of hurting other people. So we got to be very conservative here. Because remember, they can always just open and close the door themselves. This is us just helping when we know for sure it won't hurt anything. So if it's already closed and there's someone on the back pad, let's keep it closed. We don't want to just whack someone. Alright? If the door is closed and there's someone on both the front pad and the back pad, what do we want to do?
Keep it closed.
Keep it closed. If the door is closed and there's nobody on the front or the back, what do we want to do?
Keep it closed.
Keep it closed. So this is what we would want our little machine that we designed for this door to do. Here's all the possible inputs it receives. Here's all the possible states it can be in. And then we just drive some mechanism now to actually open or close the door based off of what state it was in. Right? So how do we represent this now with a state machine? Here's how we do it. For each possible state, we draw a circle, kind of like drawing a graph. So this one represents the state open. We'll do closed here. Closed. This one represents the state open. Okay. Now, on closed, if we get input from the front, we switch to open. So closed, if our input comes from the front, we switch to open. So we label this arrow front to specify that's an input our machine could receive. So we're going to label each edge in our directed graph, if you want to think about it that way. So it was in the state open, or it was in the state closed. If there's input from the front, we switch to open. In the state closed, or if there's input from the back, we stay closed. If there's input from both, we stay closed. And if there's input from neither, we stay closed. So if it's this, or this, we stay closed. But if it's just the front, we switch to open. Right? Similarly, in open, if there's input from the front, we stay open. If there's input from just the back, we stay open. If there's input from both, we stay open. And if it's neither, we switch to closed. You with me? So notice that the labels on all our arrows were the inputs we could receive, and what we wrote inside each of these circles were the possible states of our system. You with me? So this is very close to what our finite state machines are going to look like. That was an example just to help give you some intuition. Now let's get into an actual finite state machine. So now we're going to design a finite state machine which is going to recognize binary strings with an even number of zeros. Okay? So, what do? We're going to draw out our machine with, in this case, we only need two states. This state is going to keep track of an odd number of zeros. This state is going to keep track of an even number of zeros. Okay? We'll call this state whatever we want. I'll call it Q0, and I'll call this state Q1. Why? Doesn't matter. They're just names. And may call this one, not this one, even number of zeros. This one, even number of zeros, odd number of zeros. We want to accept strings. We want to recognize strings. We want to get strings that have an even number of zeros. So this one's going to have two circles, which means it's what we call an accept state. So this is my state for an even number of zeros. This is my state for an odd number of zeros. If I have an even number of zeros and I read a zero, how many zeros do I have? Losing you?
Yeah, one.
We now have an odd number of zeros. And if I have an odd number of zeros and I get an input of 0, I now have an even number of zeros.
I see.
You wrote 0 on both ones. What does 0 mean?
Zeros are going to be our inputs. So maybe I should just fill out this machine without any input from you guys. And then tell you what it means. And show you the strings it accepts. Okay, so I wrote an external arrow pointing to this state. That external arrow means this is where we start.
A what arrow?
External. An arrow that didn't cover me.
External, yeah.
That's our start arrow, which means start at this state. Now, we're talking about binary strings, so now our input. Down here, our input was front, back, both, or neither. When your input is binary strings, then your input is going to be some binary string. It's going to be something like 0, 0, 1, 1, 0, 1, 0. Does this have an even number of zeros?
Yes.
So I want my machine to accept this string. Does this have an even number of zeros?
No.
So I want to not accept this string. So this is our input, and we think about reading one input at a time and changing our state accordingly. So we start here. First we read a 0. You with me? So since we read a 0, where do we go from this state on a 0 to this state? Then we read another 0.
And it goes back.
Now we're back. Then we read a 1. Sorry. On a 1 we stay here. On a 1 we still stay here.
Yep.
On a 0 we switch.
Yep.
On a 1 we stay here. On a 0 we switch.
Yeah.
If we end in the accept state, then we accept the string. Accept state means a state with two circles. So this string gets accepted by our machine.
Yeah.
Now let's try this one. We start here. We read a 0. We read a 1. We read a 1. We read a 1. We read a 0. We read a 1. We read a 0. Is that an accept state? No. So we reject this string. So all the strings that would be accepted by this machine, all the binary strings that would be accepted by this machine, have an even number of zeros. Does that make sense? And those will be the only strings accepted by this machine. If it has an odd number of zeros, it won't get accepted.
So are we going to, in the future, go with the formula for what that picture means?
Yes. The same way that we started with this and we were able to construct this, we'll get a formal definition of this thing, precisely what it is. Kind of like when we did graph theory, we have the picture of the graph and then we had a precise definition for the graph. This is the picture version of our state machine. We'll give you an exact definition in a sec. We want to get comfortable with the intuition first, because the definition is kind of big. Make sense?
Yeah.
Okay. So you see how any binary string with an even number of zeros would end in this state, and any binary string with an odd number of zeros would end in this state.
Yeah.
So if we were to create a set of all the strings accepted by the thing, so it accepts 0, 0, 1, 1. Now remember what we tested, 0, 1, 0, something like that. It accepted that one. And it would also accept 0, 0, right? And it would also accept 0, 1, 0, right? And it would also accept the empty string, right?
Yeah.
How many zeros in the empty string?
0.
Is that an even number?
Yeah.
0's even. Yes. And dot, dot, dot. So the set of all the strings accepted by this machine are right here. That we call the language of the machine. All the strings it accepts. What's a language? It's a set of strings. And the alphabet, it was implied when I said binary, that our alphabet here, was equal to the set 0, 1. And that'll be our alphabet most of the time. Okay? All right, let's try another one. And this time, have you guys see if you can come up with it. So we want to come up with a machine that recognizes all the binary strings with 1, 1 as a substring. Or in other words, a 1, 1 shows up in there somewhere.
Together?
Yeah, 2 1s in a row.
Can we use like 3 of those circle
You
things?
can use as many of those circle things as you want.
Does the answer include 3 circle things?
There isn't one right answer,
Oh,
typically.
okay.
Okay, so she's saying we want 3 circle things. And we'll say we start this one, okay. And we'll just label them Q0, Q1, Q2. Q is a common variable name for a state. All right, on this one, on a 0 or 1, what should we do? On a 0,
You just stay in the same one?
on 0, we say we stay here. On a 1,
You go to Q.
we go here. So we've seen a 1 so far,
Oh, yeah.
but not a 1, 1. In Q1, if we read a 0, what should we do?
Go back to
Go back to Q.
Go back. We got to restart and re-look for our substring. So that goes back to here. Sorry. Usually when you do arrows back and forth, you curve them like that. In Q1, if we saw a 1, though, where do we go?
Q2.
To Q2. And at this point, we've seen a 1, 1, right?
Yeah.
So this one is our accept state. Sorry. And once we've seen a 1, 1, then it doesn't matter if we see a 0 or a 1, we stay here, right?
Right.
Yeah.
And let's just test on a string just to make sure. So we'll try 0, 1, 0, 1, 1, 0. Right? So we start here. On a 0, we go back to here. 1, we go to here. 0, oh, gotta restart. 1, we got to here. 1, yes, there's our substring, we have it. Now we read a 0, we're still here. Good? Okay. Cool. So that's a finite state machine. Not too bad, right? Okay. Now our definition. We call that a finite automaton. That's what these two were. And I'm going to loosely say finite state machine over and over again. All right, so what's a finite automaton? A finite automaton is a 5-tuple, a list with 5 elements in there. We call them Q, sigma, delta, Q naught, and F, where Q is a finite set called the states. So Q is a set of all our states. Sigma is our alphabet, our input alphabet. Like here it was 0 and 1. So here, capital Q was the set containing Q naught, Q1, Q2. Sigma was a set containing 0 and 1. Delta is our transition function. So delta looks at your state and the symbol you're looking at and determines your next state. It has 2 inputs and gives you 1 output, a lot like this table. This table, you took your current state, like open, and your current input, like front, to determine your next state, open. So here, this function f took open and front to determine open. So it takes a state and an input symbol to determine the next state. Your delta takes a state and an input symbol, and it spits out the state. And you need to tell it what to do for every possible combination of state and input symbol. So you need to take the cross product of those 2 sets. Remember what this is. This is a set of all ordered pairs where the first element comes from that set and the second element comes from that set. So you need to know what to be able to do with every possible state and input symbol combination. And it will give you out some other state where you should transition to. Does that make sense? It's exactly what we did with that table. Okay, so delta is your transition function, and it maps from your set of states crossed with your alphabet to your set of states. Q naught has to be an element in Q, and it's your start state. It's the one that gets that little arrow. And then finally, F is a subset of Q, and it is all your except states. In these 2 examples, we happen to only have 1 except state. You could have many except states. You can only have 1 start state. It doesn't make sense to start in 2 different places. It does make sense to accept from 2 different places. Make sense? All right, so let's now write these out explicitly. M1. This is equal to the 5-tuple, where our first element is a set of states. Our set of states in this example was Q naught and Q1. Right? There was our set of states. Comma. Our alphabet here was 0, 1. Those were our input symbols. Right? Our transition function we'll define to the side. So we'll just put it in like that and then define to the side here in a sec. Our start state was Q naught. You don't have to call your start state Q naught, even though it showed up at Q naught there. I could have just as easily called this capital A and put a capital A here. And then finally, the set of except states was the set containing Q1. So M1 is equal to this, where delta, we'll write delta out explicitly, where, and then usually we'll use a table to represent delta from here on out. But let's just write one time explicitly just to make sure we're very clear. Delta is equal to the set of ordered pairs, where our first thing is an ordered pair. It's a cross product between our set and our language. So on a Q naught and a 0, we go to what? Sorry, switch this back to Q naught.
Go to Q1.
On a Q naught and a 0, we go to Q1, comma. On a Q naught and a 1, we go to Q naught. On a Q1 and a 0, we go to Q naught, comma. And then on a Q1 and a 1, we go to Q1. Okay, so there's delta written out explicitly. Notice that delta is a map from this set crossed with this set to this set. Maybe write that out explicitly once. In this case, Q cross sigma is equal to the set of all the ordered pairs where the first thing comes from that and the second thing comes from that. So it's Q naught, comma, 0, Q naught, comma, 1, Q1, comma, 0, Q1, comma, 1. So this was Q cross sigma in this example, and delta has a domain equal to that. So your transition function has a domain of Q crossed with sigma. Notice that the domain of this function is this set right here. It's all left-hand elements. That thing, that thing, that thing, and that thing. And it maps to Q. Notice all the right-hand elements are in Q. So it maps everything in this to something in just Q in that. That makes sense? It's kind of a dense definition, but once you get it, it's simple. It's just dense. There's a bunch of pieces, but they're pretty straightforward pieces. Because it's just capturing, that nice simple picture. All right, so let's try it for M2 now. Let's write out what M2 is. And we'll write that over here to the side. So M2 is equal to the 5 tuple. What's my set of states?
Q naught, Q1, Q2.
What's my alphabet?
0 and 1.
Transition function, we'll write that with the table. And
Q naught starting.
Q naught was our start state. And then our set of accept states was just Q2. Notice, in our definition, set, function, state, an element of Q, and then subset of Q. Right? Okay. Where delta, we'll represent delta now with the table to the side. Let's see. All our possible states were Q naught, Q1, Q2. And all our possible inputs were 0 and 1. Right? And on Q naught and a 0, we got Q naught. Q naught on a 1, we got Q1. Q1 on a 0, we got Q naught. Q1 on a 1, we got Q2. Q2 on a 0, we got Q2. Q2 on a 1, we got Q2. And we see how this is representing a function, right? Whose domain are these ordered pairs? Okay, perfect. Now, there's that. Now, let's do it the other way. Let's go from a precise definition to drawing the picture. Because we should be able to go back and forth, right? There should be equivalent ways of talking about the same machine. So now you've got the machine M3 is equal to, the states are Q1, Q2, Q3. Your alphabet is 0, 1. Your delta function is right here. Your start state is Q1. Your accept state is Q2.
Okay.
So drawing out the picture, we have 3 states.
Yep.
Q1, Q2, Q3. Which one's our start?
Q1.
Q1. What's our accept?
Q2.
Q2. All right. On a Q1, when I read 0, where do I go?
Q1.
Where do I go on a 1?
Q2.
On Q2, on a 0, where do I go?
Q3.
And on a 1, where do I go?
Q2.
This could be the right one. On a Q3, on a 0, where do I go?
Q2.
And on a 1?
Q2. Again.
So you can comma separate them if it's what it does for both of them. Make sense? So we went from a precise definition to this picture, and we know how to go from this picture to a precise definition. So they're logically equivalent. Typically, we want to work with a picture rather than the precise definition for obvious reasons. Right? Okay, cool.
Is there like a significance to that machine?
Oh, was this machine accepting?
Yeah.
Yeah, what is it accepting?
Ones, one is zeros in Q3. 1, 0, 1, 0, 1, 0.
You say it's accepting.
We'll accept that, yeah. No.
I see. Right here. 1,
Oh, that's another one.
0,
Or another 0.
1, 0.
Let's add another 0, 1. What? Now it'll work. Now you just messed it.
Will this get accepted?
No.
Why not?
Has to end in.
No. Because it has an even number. No, it won't, because it does have an even number. And it starts out with 1, so then it needs an even number after the 1. So you need to add
So
a
it
number.
tracks even numbers as long as it doesn't start with 1.
It tracks.
Oh,
It's what?
after the 1, it tracks even numbers. After the first one, it
What
tracks
do you
even
guys
numbers.
mean by even numbers? Like,
So it tracks
Even amount 0 months.
an even number of zeros after the first one.
Yeah.
So if I do 1, 0, 0, 0, 1, 0, 0, 0, will that accept?
If that's an even amount of numbers. No.
Oh, an even amount of numbers or
After
zeros?
the 1.
Here's a 1.
So yeah, after that. So now that's 7 numbers after the 1. So that will not accept.
Oh, so if I would have done 0, 0, 0, 1, 1, 0, 0, 0. Now
That's
will
not true, though. That's a 0, not 0 and 1.
Once only.
it will accept ones only. Will accept this string?
yeah.
No, you have to do. Oh yeah.
1, 0, 0. Yeah.
So it needs 100.
Will accept this string?
No.
No.
So it needs 1, 1. After the first one, it needs to go 0. If it goes 0, it needs to have another number after it.
It has at least 1, 1, and ends in an even number of zeros.
After the first one, it has to after
It has at least 1, 1,
Oh,
and
shit.
ends in an even number of zeros. That's what it accepts.
That's what I said the first time.
Sure you did. Okay, so yeah. Now what you guys were just really trying to do is great, because you were trying to come up with the language of the machine. So definition. If A is a set of all strings accepted by some machine M, this we call machine M3, this one we call machine M2, this one we call machine M1. So these we call these things machines. So if A is a set of all strings accepted by some machine M, we say that A is the language of the machine, or that M recognizes A, or that M accepts A. Those are all logically equivalent ways of saying the same thing. And we write the language of M is equal to A. Going through it, the language of M1, the machine we had right here, was an even number of zeros. The language of this machine right here was a set of all strings W, such that W contains a substring 1, 1. This machine here was a set of all W, such that W contains at least 1, 1, and ends in an even number of zeros. I said or 1 in case you didn't remember that 0, zeros is an even number. But we already had that discussion, so I can get rid of that. So it ends in an even number of zeros. So we pick any random string, 1, 1, or 1, 0, 1, 1. This ends in an even number of zeros, so it will be accepted by that, and it has at least one 1.
What if you get 1, 0,
1, 0, 1 does not end in an even number of zeros. It ends in an odd number of zeros.
1? Yeah, that would work.
1, 0,
1.
1, 0.
No, 1, 0, 1, just that. That's not even number of zeros.
How many zeros does it end in? No zeros, which is an even number. Ends in 0 number of zeros. If that confuses you, put it back how I had here. Or a 1, if that helps.
So why do you need the even number of zeros? Because it's always going to be the even number of zeros.
It will accept this string, because this string ends in no zeros. So an even number of zeros.
Oh, I see.
It will not accept that, it ends in an odd number of zeros.
So at the end of it.
Will accept it. Won't. Will.
I see what you mean.
Still will. Still will. Still will. Won't. Will. Won't. Will.
Yeah, I see what you're saying.
Okay. Yeah. There's going to be a lot of getting used to the language that we talk about. Unfortunately, none of you are coming from a programming background, or at least Anna might already be comfortable with strings, but typically when you teach in this class, people programming already know what you mean by string. It's very intuitive because it's one of the basic types you work with in programming. So, yeah, we're going to have to get used to the language here. Anyways, there we go. There's our first little taste of it. We'll continue with this next time. But yeah, now we're finally getting into some of the material and the type of thinking you have to do to solve the problems. Any questions about any of this so far? Surprised my voice hung. I thought I was going to lose it.